Okay, so we have this next question right here. It says the diagram shows a crane lifting a load. There's a large mass called counterweight attached to the crane on the opposite side of the tower. The crane has a electric motor with an efficiency of 47%. The crane lifts a load of 4.4 times 10 raised to power 4 Newton. The load moves through a vertical distance of 15 meters in a time 70 seconds. Determine the average power input of the electric motor. Okay, so one thing I want to mention is that this thing, counterweight, is just a distraction. So just avoid this. Understand what values you are given, right? So first step, understand what values are given, right? Note down what values are given. Understand the values given. Okay, so I have force, I have the height, okay, because it's lifting load from here to here, 15 meters, right? Height is 15 meters. So you have force, you have height, you have time, and you have efficiency's value, which is 47%, okay? And it's the, yeah, it's the efficiency value. So now you need to find average power input. Just remove average so you're left with power input, right? So if you use the efficiency's formula, right? Efficiency is equals to useful power, right? Over input power, or you can say the total power, okay? So efficiency given, you need to find useful power. How we will find useful power? You can see that this box was lifted 15 meters above the ground in 17 seconds, right? So we can use power formula, right? Power is equals to W by T, right? To get this power, right? To get this input, sorry, not input, my bad, useful power, okay? So to get this useful power, you need this work done. Work done, in other words, is also energy. So there are actually two ways I can see that. You can use one of the this formula, F into displacement, change in displacement. But like honestly, like the way I understand it, just make it simple, right? So if you can see there's a change in height, instead of what, you can use this and you will still get the same answer, okay? But what I prefer is that understand simply, right? So you're moving from the box from ground to above level with the height. Whenever an height is mentioned, I always think of energy, and energy's formula of gravitational potentials energy, right? Gravitational potential energy, which is mgh, right? So you can use this formula. I recommend you can use both, right? But I recommend thinking simple, and whatever comes in your mind first, use that, okay? So this thing came in my mind first, so I'm going to use this. So for mass part and for gravity part, let's see. So mass and gravity can be written as W and H, right? Weight and that stuff. So you have been given that this weight is 4.4 times 10 raised to power 4, right? And then you have the height, which is 15 meters, okay? So if you calculate this value, you will get 6.6 times 10 raised to power 5 joules, okay? Now you can use this joules in power's formula, right? So, okay, let me write it down here as well, so it's much more neat. So, gravitational potential energy, let me write it like this. Gravitational potential energy is equals to mgh. You can also write it as wh, because w is equals to mg, right? And you have weight, you have basically the weight of it. So it's 4.4 times 10 raised to power 4. Height is 15, and the rounded off value I got was 6.6 times 10 raised to 5 joules. Don't use rounded off values. Better to use the value you have been given. I don't have a calculator right now with me, so I've already written the value for it, right, in a rounded off version. So now the next part is that what you need to do is you need to use power is equals to energy by time or work done by time. If you get your answer from work done, use work done. I got my answer from energy, so I will use my energy symbol here. So it's 6.6 times 10 raised to power 5 and time is 70 seconds. So now if you solve this, you will get 9.4 times 10 raised to power 3 watt. Now you can use this watt because this is the useful watt. So you can use efficiency equals to useful over total. So efficiency is 47. In other words, it will be 0.47. You don't write in percentage, you actually write in numbers, basically in decimal. And useful is, what is useful? Useful is 9.4 times 10 raised to power 3, and then you need to find total. Now, if you calculate the value for total, you will get as 2 times 10 raised to power 4 watt. Okay, 2 times 10 raised to power 4 watt. Okay, so we have this next part here. The horizontal distance from the load to the tower can be changed. The horizontal distance from the counterweight to the tower can also be changed. Explain how the counterweight needs to move when the load is moved away from the tower. Very simple, dude. Like, honestly, I'm going to explain in a very simple way. First step, okay? Identify what could go wrong. If I basically increase the right side and I don't increase, basically I change the right side and I don't change the left side, if the clockwise movement is not equal to the anti-clockwise movement, then what will happen? The tower will break and it will basically fall down, and we don't want that. So first thing we want is total clockwise moment is equal to total anti-clockwise moment. Okay, second thing, identify what is clockwise and what is anti-clockwise. Some people do make mistakes when they do not identify what is clockwise and what is anti-clockwise, and then once they figure out later on that they have chosen the wrong clockwise and anti-clockwise, they have to do the whole question again, and you don't have time in exam to do the whole question again. Okay, so further identify this, which is clockwise and which is anti-clockwise, right? Clockwise and anti-clockwise, what are those? So this is clockwise, right? Clockwise, this means basically if you see a time, it goes, it moves on the right side, it moves clockwisely. Okay, and anti-clockwise is like basically the opposite, moving the opposite direction of the clock. Okay, the seconds arrow. Okay, I'm talking about the seconds arrow. So this is clockwise and this is anti-clockwise, right? So you mentioned that our load is clockwise and our counterweight is anti-clockwise. Now third step, what is third step? So let's say for now this is 22 because it says 30, right? 30 meters, so 22. If I increase its distance, right? Let's say I make it 24, what will happen? So as you know that we have the formula F into D, right? Clockwise and anti-clockwise. Moments formula is F into D, right? And the same thing, clockwise and anti-clockwise have the same thing, F into D. So if I increase the D, basically I increase it to make it 24, then of course I cannot change force. I cannot change the counterweight's force, right? It's already up in the air. It won't automatically increase its force, right? It won't increase it. So you have to increase its distance as well. So if you're increasing the distance for the load, if you're making it further away from the tower, then you have to also make counterweight further away from tower, right? It doesn't make sense. Yeah, so we just simply have to write this whole thing and that's it, nothing else. Okay, so first step, let's write the total clockwise moment is equal to the total anti-clockwise moment. And then the second thing you say that if it is not, then the tower breaks. You can just say breaks. Okay, so we have mentioned that. Now you can say either way, which is clockwise and which is anti-clockwise. Just identify them. The load equals clockwise and the counterweight. Wait, counterweight is anti-clockwise. Okay, anti-clockwise. You have mentioned that. Now the third step is if I increase the distance between the tower and the load, the what value will increase? The clockwise value will increase. In order to make clockwise and anti-clockwise equal, we in order to make so we need to increase distance between the counterweight and the tower, right? And then increase the weight and it basically increase the counterweight, increase the distance between the counterweight and the tower so that it remains balanced. Okay, remains balanced. So simple question, and you just write the simple logical answer, right? Don't write anything complicated. It is not required here. Simple thinking, simple answer, and yeah, just portray your simple answer here, and that's your final answer. Okay, so we have this next part right here. It's a very interesting part. We have that the beam is uniform with weight this, counterweight has a weight this, load has a weight this. Deduce whether the load can be moved at the end of the beam without the crane toppling. So it's very simple, but you have to follow some steps, okay? So the first step, identify what values you have been given, okay? I always say that. Identify what values you have been given. So you have three weights: uniform beam, the beam's weight, the counterweight, and the load weight. Okay, and then you have two distances, right? We have the distance from center to counterweight and the whole, basically, is the length of the uniform beam. Now you have identified that. Remember that you have moment. You're taking moment at center, right? This is the center, right? Basically the pole. Okay, so we will do all of our calculation according to this statement. Okay, so 8 meters is from center to counterweight, right? Now second thing, important step here, read the statement again and identify if there is any hidden meaning, not normally not hidden meaning, but like anything useful that we can use for to solve this question. So you can say that, you can see that basically it said uniform, right? That's why I also highlighted uniform. Uniform means that the weight is acting at center. Okay, so center is somewhere here, because if you divide 30 by 2, it's 15 meters, right? So 15 meters come from here, whether you go from left to right or right from left. Okay, now you have to identify again what moment at center, right? We are taking moment at center, so we have to decide the how much distance it is from center to the weight of the beam. Okay, so it's easier to do it from left to right. Okay, so let's do it. Sorry, meters. Okay, so now we do 15 minus 8. Okay, so you will get 7 meters, right? So you subtract this from here, like from 15, this total 15, you subtract 8, and then you will get this much, which is 7. So this is your weight of beam. Okay, simple as that. Now that is out of the way. Now the second thing is, you need to understand that clockwise moment is equals to anti-clockwise moment, right? If it doesn't follow the rule, it will anyway will topple, the crane will topple without even moving the load. Okay, so it needs to follow that. Now we don't know what's the how much limit do we have, like from the center of the pole till the load, how much we can move, right? So we're gonna keep this thing as x, right? So we can see how much max can we move, right? So we're gonna use this formula, and moment has a formula of F into D. So counterweight is, remember that you need to also identify that yeah, I didn't write this, so identify anything useful in question. And the third thing is identify. What was I about to say? I forgot. Identify the clockwise and anti-clockwise moment, right? So this thing I wanted to say, identify your clockwise and anti-clockwise moment. Okay, so this is your anti-clockwise, okay, and these two things are your clockwise, okay. So write them properly, okay. So clockwise is what? So I have clockwise as 3.0 times 10 raised to power 4. So first we will do the beam times the distance, which is 7, and then you have plus the load, which is 4.4 times raised to power 4, and then we don't know it's x, right? How much we can go further before. If we move it further than that, it will topple anyways. Without, remember that we're not doing the previous part again. Previous part they said we can change the distance. In this part they did not say we can change the distance of the counterweight, so remove that thought from your mind, okay. We cannot change any distance for the counterweight, right? We're just only seeing that how much further can we move the load before it topples, right? Can we move it till the end of the beam without changing the distance from the counterweight, right? Center to counterweight. So you make it equals to the anti-clockwise, which is 1.1 times 10 raised to power 5 times the distance, which is 8, okay, from the center. And now if you solve this, like completely solve this, right? If you let me arrange it properly, and then we will write the answer. So it goes 1.1 times 10 raised to power 5 times 8 minus 3 times 10 raised to power 4 times 7 divided by 4.4 times 10 raised to power, sorry, wait, it's wait, how much is it? It's 4.4 times 10 raised to power 4. Yeah, that's it, okay. So now you have done this much. 4.4 is, sorry for my bad writing, it's 4.4 times 10 raised to power 4. And then if you solve this, you will get a distance of about 15.2 meters, okay. I have the rounded off value with me, so 15.2 meters. And you can see that from here to here, let me use red color a bit so that it's much more visible. So this much is 22, right, after you minus 8, right? So till the end it means that you have to move it till 22 meters, but you can't actually move it because at this point it reaches its max equilibrium, right? Max equilibrium point, how much max you can move the load. If you move further than that, it will topple without any reasons, right? You can't, remember, you can't move the counterweight, right? If it exceeds 15.2 meters, it will topple without any doubt, okay. You simply just write that 15.2 is less than 22 meters. So if we move it, if we move it means load, if we move load at the edge, the crane, it's crane, right? The crane will topple, okay. Yeah, the crane will topple, okay. Simple as that.